Hi, my name is Pramod of the CoinOp Collection, and today I'm going to show you how the second part of the video that we talked about last time, which was implementing the CVSD board for Smash TV. I have not taken a look at this in a couple of weeks since I implemented it, and the last video we created was some time ago. So I thought to return back to this because I'd been working on other projects, so I had not returned back to this recently. But So I thought I'd create a video here to kind of show you how I implemented this, and it does indeed work. All the components work, and it works fine. Now, the last time what we discussed was we talked about putting the main component IPs into the code file, which is right here, and we'll go over this code file in a minute. So we talked about laying down the template for the 6809, and then we did the 2151, and then I think we did the Paya, and then I think we made some notes about the DAX that are over here. So we did that, and we just kind of left it at that. Now, after I did that, in the process of actually implementing this, I found that one of the outstanding questions from the last video was whether the second DAC was actually used for anything. Because there's two DACs on this. There's the 3012, the YM 3012, which does work hand in hand with the 2151 over here, and that DAC is often paired with the 2151, so that wasn't a surprise. But then there's this other thing called the 1408 P8, and that is over here, right down here in this corner here, U11. And the question was whether that was used or not, because it was strange how they included it on the board, and it clearly is connected to the parallel interface, peripheral interface here, chip, that is the Paya, but I didn't know whether it did anything or not. And sure enough, what I found was when I had implemented the thing and I started up the game, I was getting sounds. So I got the sound effects. So the sound effects are produced by the 55516 chip, or the 55564 chip, which is right here. That's fine. That's speech, right? I'm sorry, not sound effects, but speech. And then the synth is produced by the 2151 in accordance with this DAC. This DAC is actually integrated in Jose's 2151, so I didn't need to wire that differently or wire it externally. It's already embedded in there. And then there's this other thing, this 1408, which I was questioning. I was like, what does this even do? And so when I booted up the game, I found that the bass, which are the instruments for the music, were totally missing. And the bong noise at the beginning when you start up the game, and it goes through the VRAM checks, was not there. So I was like, okay. And so I went to the emulator. So usually what I do in those cases is I try to load up a working software emulator version of the same thing, just to kind of confirm that what the use of that chip is, or that component is. And sure enough, when I commented that out, I was able to confirm that does produce the instruments, and the bass for the music samples, and also the bong noise in the beginning. So I was able to create that DAC, because that DAC IP does not exist anywhere. So I had to go ahead and create that. So I did that. It was relatively simple, and I'll show you that in a few minutes how I did that. And other than that, a lot of this was pretty straightforward. This is one of the easier soundboards, I think. There's I think two variants of this. There is the CVSD soundboard, and then there's another one that uses 80 PCM for samples as well. So that one is kind of similar. It just uses a different form of communication back and forth to the CPU. So I'll show you that in a minute. Okay, so where do we start here? So we started off by adding these IPs to the code file, and we started out with kind of just adding some notes on what these interfaces are. So let's go through the code file, and I'll show you step by step how they relate to the schematic and what sort of strategies I use and patterns I use in the Verilog to implement them. Okay. All right. So this is the module here, and I have a few related files open up here that are the submodules, or that are instantiated by this module, and I'll show you those in a minute too. Okay. As we go along. So let's start with the top level. So let's start with the interface of the module. So the interface of the module includes a clock input and a reset input. So this is a global reset, and this is the master clock. So the master clock is the single clock that drives the whole system, right? From there, you should create clock enables based on your master clock, which will effectively achieve the speeds that you want to achieve for the various components that you are instantiating or using, right? And those components are the 6809. So the 6809 is 8 megahertz, right? So we use a 8 megahertz clock. So when we do this, basically we pass the master clock. So we trigger on the positive edge of the master clock, and then we check whether this is also is high, right? So if you check if the clock enable is high and the master clock has a positive edge, that condition will be triggered. That's basically like that, and then that'll be equivalent to 8 megahertz, right? Because you're basically dividing this clock by however much it takes to get an 8 megahertz clock enable, right? So that's how that works. So 6809, and then we have the 2151, which uses a couple of clocks. It uses a 3.57 and a 1.78. This is actually half of this, so it works on the half clock. Then we have the interface to the CPU, which is the talkback. The talkback out is something that's not used on this board. It's used in the ADPCM board, but basically it's used for the soundboard to communicate back to the CPU what the status is. The talkback in is a sound command that's received from the CPU to the soundboard to play a sound or music combination or whatever it's trying to do. And we'll go through the format of that in a minute. And notice I put the pins here that I found on the schematic just so I know what the pins do in the talkback interface. So the talkback interface is right here in the schematic. It's right here on the bottom. You see CPU data interface right here. It's shown. So you see like these pins here. These pins are not connected. This pin is a reset pin. And then you have like other pins like data, and then CB1 and CB2, which go to the PIA. So all of those I've modeled out, and I've made notation of them, and you'll see them later on. And then I also have the interrupt here. So what's interesting is if you take a look at this schematic and you follow this pin all the way down, right? The one pin that is there, that's not really, it doesn't seem like it's connected to anything, which it doesn't do anything in this board. But what's interesting is it actually connects to a pin called sound in. So if you go down and like check it, right? Well, I have to go pretty down for this. So let me go down here. I'll show it to you in a second. I think it was on page, it was one of the last pages. I know it was on this side of this. Let me see. Whoops, did I miss it? Okay, so here's the soundboard interface, right? So they provide two interfaces. So in this case, I actually have to look on the real board because I don't know what interface it's talking about. Like there's a J8 and there's a J9, and this says alternate pinout. So I have no idea what it's talking about. I don't know if this is wired. I don't know if this is something else. So I actually pull out my board and I start checking it, right, physically. And what's interesting is, so this J9, this series of pins actually exists on the board, but it's not, there are no pins soldered to them, right? There's no pins that are connected to this. And it's interesting because I don't know if there are revisions of the board that do have that, and if they do something different, or maybe there was another soundboard that was that was in the beginning, or another revision of it that accompanies this pinout. But this thing is totally like there's nothing in there on my board anyway. And this is the real interface we're talking about on the right hand side. So you see here, like this pin 12 goes to snd.int. And what's interesting is that goes to the auto clear PLD. And the PLD itself, in turn, goes back to the interrupt 2 pin on the CPU. So I was thinking, okay, well, maybe this is generating an interrupt somewhere. This is supposed to generate an interrupt on the CPU. But actually, it does not do that. Interestingly enough, it sends an interrupt request to the PLD, and the PLD in turn generates the interrupt to the CPU. Well, I mean, if it needs to, but actually in this whole scheme, it doesn't do anything. So no interrupt is actually generated from the soundboard. It just works independently for some reason or another. So that was an interesting thing because like most of the sound implementations I've worked with in the past usually generate interrupts to synchronize the CPU. Like, because sometimes if you don't have the interrupt connected properly and they're not in sync between the sound circuits and the CPU part of the system, usually like the sound goes out of sync or the sound like has some weird like effects that come up because it's just struggling to keep up. Usually, an interrupt will regulate. I'll tell the CPU, "Hey, slow down. We're still playing sounds here," or like speed up. Like just regulate it. So that it stays in sync. But I guess in this case, none of that is actually hooked up. So I hooked that up, but I did actually connect this, but I found that it didn't really do anything. So I just left it disconnected. Um, the next series of pins have to do with the ROMs. So the ROMs that you see here, uh, in this here, the U4, the U19, and the U20, those obviously have to come from SD-RAM, right? Because that's where we're loading our ROM to the start. So this will allow it to address the ROM and then also get the data out from it. And then these CS and OK signals tell the SD-RAM implementation that I did in another module. There is a request going on to get data out, and this will tell me when the data is ready to be read and it's valid on the dout line. Okay, and then we have the mixer part of it. So the mixer basically is to the top level of the core, right? So the mixer will go to the MR framework, as you might call it, right? So the MR framework has like left and right, and then sample and peak, right? It takes in all those signals and it actually outputs sound, through HDMI or wherever your audio thing, your DAC or wherever the audio is. And maybe it does some further processing, but I don't know really much about the MR framework layer of that side of it. But yeah, that's basically what that does. This is the final left and right sound that is output to the top level core, and it plays the sound on your TV or whatever your speakers. There's two other options, which is game and FX level. FX level allows a user to is a special thing that allows the user in the GUI that I added to adjust the FX level of the game. So that's like your boosting of the normalized sound, right? So you're going to you're either boost the levels of it, or decrease the level, or it stays normal, or it goes under. So that's what FX level is, and you'll see this option very commonly in in the rising cores. You'll see that. You'll see it in a few other cores, but it's just an option that's a user defined option. And game is something that I always propagate to different modules, because for like when we're creating a multi-game core, we have to have a way of distinguishing what game it is we are configuring the hardware, to play, right? And so there might be different logic or different sorts of things that happen depending on what game you're playing in a multi-game core, right? So I have this game signal here, and as you can see, like these are the games that I support. So this game signal is actually in the MRA, and the MRA will send 1 byte at the start, which will set this game signal in the loader. Right, there's a loader, and it will just configure itself and do that stuff, in the whole thing. Okay, so here's the first part. The first part of this file has the mixers. So where's the mixer? What is a mixer? Well, let me show you on the schematic. So the mixer is basically a thing that muxes together all the sound, the aggregate sound. We call it the aggregate sound of all the components together, um, on a frame and just outputs it right somewhere. So you can see there's a mixer interface right here, right? There's a mixer circuit right here, right, where it says CPU sound, about right here and right here. And as you can see, right, all these components outputted to these set of analog circuits, and eventually they go out to the audio on this board. So this is a mixer circuit right here. Okay, and the way we do that in Verilog is not dissimilar to that, right? So there's a module in JTFrame called JTFrame Mixer, and you tell it what the bit width of the sounds that you're supplying are. So most of the time we're working on signed 16-bit sounds. And we're outputting signed 16-bit sounds. So that's what I've configured this as. So as you can, and I have two of them, one for left and one for right, right? Because if your game is stereo, you're going to have different outputs on the left and the right. If it's mono, then you'll just have the left, and the left will replicate itself to the right, right? You'll use the same output. I have the left, right, the final left, right, which comes from the YM2151. I have the final HC0, which it comes from the 55564. And then the final DAC is the 1408 sound that's here. So all these three sources are mixed together in aggregate, and it outputs on the left. You see the mixed signal here? It outputs on the left. And this is the gain for each channel that I mentioned, like the FX level boost that I have here. This is the gain for each channel. And for the moment, I'm just using the booster for the voice and the instruments. I use a standard one for the synth. So it's FM gain right here, which is 4. I don't know. I've just used this for now. I usually go through a cycle where I try adjusting the different levels and all that stuff, because sometimes people like the bass to be more punchy, so they want a higher level of volume on that. Sometimes people want the speech boosted. So there's all different kinds of people who perceive sounds differently, and so we go through a cycle where, and that seems to be like a big pet peeve of a lot of people, like the sound levels. So I usually try to go in and try to adjust them properly. I don't usually go taking measurements on the board for sound levels and all that stuff. I think that's a waste of time, because the way that people perceive sound is personal to them. And so I think the way that I configure it is the way that sounds the best, I think, generally. And then I try to add FX boost options to cover the different sound levels that people might want to do. Sometimes some games have like software configuration in the CMOS menus or the BIOS menus to configure the sound levels, but I don't think the games. Well, actually, you know what? The Midway games kind of do have that for some games, not all the games, but normally I try to add an option in the user-defined menu for that. So that is left and right. Okay, so you have a mixer, and that's left and right. Now, the next thing we get into is protected RAM. There is protected RAM on the board, and so that actually appears in the region, in some region of U5, right? And so that's where the SRAM is on this board. And so the details that are in these different addresses, right, for the sound protection, this protected RAM, actually I got from the emulator implementation. So I would actually pull up Final Burn Neo. I would take a look, what is this sound protection thing, and I would get the addresses from there. It's not possible to really work out what these address ranges are, or what data they contain, solely based on the schematic, because it is a software driven thing. So software presumably loads these at the start, and in a clear state, and it reads back from them and writes back to it interactively when it's trying to test the component exists or the protection is intact. So these are the kinds of things you have to really debug the software for. It's not really a hardware type of thing you can discern from the schematics. or pulling different chips on the board. So I just take this from the emulator because that's the best source of it. That's a reverse engineering thing that comes from there. This was coded to be agnostic to the game that's there, because as you can see, there's different ranges for the different games, right? Most of them have the same length, but the maximum length is 44 bytes. So I created one that's 0 to 43, right? This RAM here, and then I have different start and end ones that I have here, and then I load it later on, which I'll show you. So when I actually load the data in, so that I also have to load up the emulator and also see what kind of data is loaded in here at the start. And it's basically like I have to take a look at the clear state and load the proper values into this protected RAM at the start. Otherwise, it won't work, right? Okay. So the next thing is the 6809. So the 6809 that I have here comes from JT Frame. So this is a wrapper around the MC6809i CPU IP that's been around for forever, right? So this is a wrapper around it that kind of does a few cool things. So first of all, the RAM is embedded, and so all you have to do is define what your RAM width is, which it's 12 in this case, right? Because we counted that in the last video, right? When we took a look at this, we found that the addresses go from A0 to A11 here, right here. And so that's 12. But I think realistically, the game does not use that. The game uses only a fraction of that, actually. So I think it does not use all 12, addressing, or the full RAM width. It just comes with more RAM than it actually uses. And then the reset signal here, I took from wherever this is wired up. So you see here, like you see this reset here, this signal here, this is the CPU. So you see this reset line goes here, it goes up, right? And you can see that this is a global reset, right? So it goes all the way down, right? All the way down here. And then it goes all the way to the interface. So you see this interface here. So the actual main board of the CPU through this talkback interface determines when a reset is actually propagated, and so that's why I have this reset 6809 one over here, and also I've added the global reset here. So this is the global reset, and this is the actual one coming from the talkback interface. So handle both conditions, because sometimes for some games, I mean not this game, but like for some other games, the CPU program resets the CPU of the sound in some random places. Not only at the start of the game, it happens like in the middle of the game too sometimes. Actually, no, it does happen in this game. It happens when so there is a startup where the bong noise plays, and then after the post, so after you get to the high score screen of Smash TV, you'll hear another set of bongs, and that is the talkback interface resetting the 6809. Okay, because when you reset the 6809, that's when the bong sound plays every time. That's like its own post or way of posting. Okay, and then we have the clock enables that we saw above, right? And then we have the interrupts. So the interrupts, the fast interrupt and the NMI, right? Those appear as pins over here. So you see here, there's FIRQ, which is fast interrupt request, and NMI, right? And they go directly wired into the NMI and the fast interrupt request here, and they go straight across into the PIA. So the PIA is the IRQ-A and IRQ-B signals coming out of it, and this is what you'll see somewhere below, is I have this in there. And then the IRQ-ACK is the acknowledgement, which I don't think is actually used, but I just have a wire placeholder for it anyway. And the rest of this stuff, there's no bus sharing in this scheme. So as you can see, like the bus sharing is actually not connected. That pin's not connected on the CPU. So you can see that right here. It's busy. It's not connected. And then After that, you have the run-of-the-mill signals. Um, so you have CPU address, the address that's coming out of the CPU that's requesting, whether it's a read request or a write request. Uh, VMA is not connected. I just thought I'd add it anyway, but it's not connected. See, VMA is not connected. And then you have RAM select, ROM select. That'll tell it because since this is actually managing the RAM, this wrapper is managing the RAM and also requesting to ROM, and it uses that to track the recovery too, like the recovery it should apply. If it should recover cycles or not. Then you need to tell it when it's RAM or when it's ROM, and also supply the OK signal for the ROM so it knows exactly how much time was spent, to retrieve that, and it compensates and does recovery of the cycles properly. Okay. The next series of pins are basically data pins. So this is the D out from the RAM. This is out from the CPU. This is into the CPU. Okay, and that's pretty straightforward. So since this is managing the RAM, right? You have a case where like this wrapper is actually going to output whatever is in the RAM contents of whatever the address is here, right? But then you have to feed that potentially back into the CPU on a different port, if that makes sense. But yeah, I'll show you that down in this file. And then you have the address bus implementation. So the address bus implementation is these bus lines right here. You see these arrows and that sort of thing. This is the bus. This is how different components get addressed on the thing, and this is how the CPU addresses the different components on this board. So through the address bus, the CPU can access like ROM potentially, this PIA over here, this YM2151, like all these components, all these isolated components is controlled by the address bus. So that's what that does, and these are a bunch of signals that control that. So usually how I implement the address bus is in this one, so it's combinational, and I usually check whether the address is matching some mask. Usually that's what I do, and I try to do it by bit selecting, but sometimes that's not always possible, right? And we have to actually check a range. So for example, for protected RAM, it's not possible to use a mask there because like if you take a look at these, like it's pretty. I mean, you're not going to be able to come up with a mask that satisfies this really in all cases. Like it's not generic enough to do that. And plus, it's a range. It's in between this and this. So since these are two like seemingly random addresses, like it's not really going to work out. So what I would do there is do a greater than or equal to and less than or equal to for that range. But if I can do a mask, I prefer to do a mask because that is easier on timing. It just takes less resources to do this compare than it is to check a range is bigger or smaller, from a logical element perspective. So, and you can actually work these out. You can actually work out what these masks are by looking at this schematic. It's not always true though, because sometimes, especially in the rising boards, they actually use a custom chip to generate addresses. So you can't work it out from the schematic. In this case, they do not do that, right? They use a bunch of logical components and multiplexers and all that stuff, right? So I'll give you a perfect example here. You can see that the A0 and A1 goes here, right? Well, actually, let me go back to the code and I'll show you I'll show you how you can work it out. So, the CPU wants to address the PIA if the 15 to 13 pins on the CPU address are in the sequence of low, high, low, right? So we're looking for A15 to A13, right? So if you take a look at this, right? You take a look at A15 to A13, right? A15, 14, 13, right? So, and if you take a look at this logical component here, you'll see that it is actually outputting when it does it does output the sequence of 0 1 0 on these three lines out, and then you'll see that it does indeed uh, perform a select on this chip here. So that's how you can work them out, by simply following the ones. The same thing for A11 and A12 here, and A0 and A1 here. So A0 and A1 go here, and those are that determines the address. There's like in this PIA, there's like different registers that get addressed, and I think there's like 3 registers or something that are addressable. So that's why it's A0 and A1 that go here, and these are the address ports. So you can actually work all this out from the schematic. It's just more work. So usually I don't do it that way. Usually I will follow an emulator because it just has it plainly written out, and I don't have to like go reverse engineering or just like run through the schematic. I do confirm in the schematic that that's indeed the address. I mean, if I'm having problems, I will do that, but normally I would extract this information from a current implementation of the emulator because that's what that's best for. Okay. So that's how you implement that. Usually I would do a combinational thing. And this is these are CPU DN. So usually when I do the CPU DN, I will use a clock enable, because what happens is CPUs run at a particular speed, right? And so when you're giving it data back, or yeah, actually when you're giving it data back into the CPU, what can happen is if you're running too fast, the same thing gets repeated multiple times. And so depending on what the implementation of the CPU is, that might actually go badly for you. It might screw up something. So what I do is I usually clock enable that. And I usually, in this case, I'll use a send2 because that is the one that's outputted from the CPU as the clock that it's operating at. Oh, this is the Q, I believe. So this is the Q signal, right? So you see like here, you'll see there's a Q and an E. These are clocks, right? They go over. These are generated clocks that operate. The E is, I think, shifted off. It's the same speed as Q, but it's just shifted off by 1 or something. Shifted off by some amount. And you can see like the E. See, it goes here. So that's a shifted clock. And then the Q is the normal speed, so gets propagated throughout the different there's some of these are flip-flops too. So yeah, you can tell like the flip-flops are driven by the Q edge. So I use Q, which is send2. That's outputted from the 6809, which is right here, right? 1/4 of send. That's the Q. Okay. So yes. So based on these combinational signals, it should know. So this is your multiplexer. It should know which one is which. I mean, if it's a read, right? So if it's a read, if the CPU requests a read, then if this meets the criteria, then it'll take it from this signal. If it's trying to read ROM, it'll take it from this. If it's trying to read from the YM2151, it'll take this, right? And so on and so forth. Okay. Now we get to the other part, which is the actual talkback stuff, right? And the rest of the address bus implementation. So these actually are special cases. So there's banking actually in the ROM. So since the ROM is the audio ROM is big, there's multiple banks, because like the addressable area that the CPU can actually address in the ROM is a small space compared to the whole size of what it needs to address, right? So there are these things called banks. So the ROM is actually divided up into different banks, and so the CPU, before it actually makes a request to read ROM, switches the banks of the switches this thing called the bank, right? There's a register that's located somewhere, or it could be a flip-flop, I don't know where it stores it on the real board, but it has a bank switch mechanism to read from, so it can read from different regions of the ROM and address them accordingly. So this is how you do that. Okay. And then HC55564 works kind of weirdly. So like what happens is, if the address is low on 11, then basically that's when it actually reads the data out. However, if it's not, then it will go ahead and clock it high. So actually, it's a software-driven clock. It's better to explain this on the schematic, actually. So you see here, where's that component? Right over here. You see here the U6. So you can see here that this is A11 and A12 that's going to it, right? And uh, if it's low, right? So if 11 is low, that's the time when the data gets into the chip, right? And also the clock is driven off of 11, right? So the pin 11 of the address that's coming out of the CPU controls the clock, high and low, right? But only when it's low does the data actually go into the CPU, or I'm sorry, not the CPU, the chip, the 55564. That's the only time when the data is sent from the CPU to the thing, and it's sent one bit at a time, as you can see. It's only one bit at a time. So as you can see, it's very slow. Well, not very slow, but that's just the way it goes. It goes fast, but like yeah, it's just that's just how it is. Okay, and now here's your protected RAM. Just making life easier for myself and just putting a reg for that. And then here is the 2151 that I set up here. It's pretty run of the mill, and it's wired up exactly as you see there. And then here's the PIA implementation, or the wiring. This wiring is pretty much exactly as you might see here, right? Just follow these out. These go to the address bus. These go to the interrupts, and these go to the talkback interface, and then this goes to that other DAC that I was talking about. Okay, so it's wired exactly like that. And then we have the final components here, which are the DAC. This is the DAC that I created. And then you have the 55564, which is right here. Okay, and this is a propagation of the different signals, just so the timing is correct on them. And then it's triggering the signals at the right time. Okay, so that's in a nutshell how the modules put together, and you can see piece by piece how that might work out, by looking at the schematic and kind of implementing it back and forth, in the Verilog code. I'm going to talk about a couple more points now, at the end of this. Well, this is now nearing the end of this. So I'm going to talk about the 55564. So the 55564 I got from a current implementation in Verilog that was used in Robotron, which is the same chip. Now, the problem with this implementation is that you see, like, this is like a multiply that's used here, right? And so and this is VHDL, by the way. So this is combinational. This is combinational. That's not really gonna fly, I think. So it creates bad timing issues. Like, you can't do multiplication or division in like one cycle. Like, you can't. That's basically impossible, right? Uh, and so like I that created actually timing issues for me, and I know I knew it was going to create timing issues because I've been in that situation before. This actually is treated as a constant, so this is done at synthesis time, right? It'll just evaluate this and just like treat it as a constant value. But this is actually a live calculation based on the current value of x, and s here. So what I did was and also this has other problems, is that it doesn't have a reset signal here to reset all the signals and all that stuff, which can become problematic depending on what it is. So what I did was I asked GPT to port this to Verilog so I can mess with it, and that version is right here. So it did a pretty good job. So this is completely done by GPT, and basically why I wanted to highlight this is one of the uses that I use GPT for is to port things or to understand code that's not mine. Because sometimes I'm in a situation where I have to understand some very complex code and I can't really follow it. So I use GPT to do that. I use it to port things from one language to another or rewrite it in a way that I can understand it. So I've done that here and I've made some changes. So first of all, I've implemented a reset. And secondly, I've converted the actual multiplication there into bit shifting. So it is possible. I mean, depending on what you have to do, it is possible to convert multiplication to just using bit shifting and subtraction and or addition. It is possible. And actually GPT does this, right? So GPT, I ask it to convert this x times h and s times b into something that doesn't use multiplication. It just uses the basic operations, bit shifting and or addition and subtraction. And this is what it came up with. It works wonderfully and it works perfectly. So that's the end of that. So we don't have to figure out how to do that by hand. And then I introduced assigned and unsigned signals because we need unsigned. This was producing signed before. This was producing unsigned before. We need signed. So I added that in there too as well. And it also made it so that this is synchronous. So a lot of the stuff here is not synchronous. Well, some of it's synchronous and some of it's not synchronous. So I've added that here, and this module works just fine. Okay, now on the 1408P8, what I did here was this is it. This is the whole DAC, believe it or not. It's very easy to do. And again, like what I do for this DAC is I will look at the documentation. I would also look at how the signals are implemented, and I'll come up with an equation. Now the equation has like division and multiplication in it, but again, I feed these equations to Chat GPT, and it will produce for me some equivalent that's not using multiplication and or division. And as you can see here, it does it, works perfectly. Okay, so that's an easy way to use Chat GPT for converting equations and that sort of thing. It's really efficient at that. And so those are the discussion of those modules. And then the Paya I wanted to kind of talk about a little bit because it is kind of a weird module, in that basically it takes in various signals from different ports and triggers interrupts and feeds data out at an appropriate time to some other location. So the Paya actually drives the secondary DAC, which is the 1408P8. So the data outputs from here actually go directly into here, and it's used that way. So all of this implementation is correct, but it's just a weird module because it's very hard to follow when these signals are actually triggering interrupts, and when the interrupts get triggered is actually a big problem on this board, I found. So I had to adjust the timing of that a little bit carefully and monitor it in the simulation bench a little bit more and try to figure out what timing it's using. Yeah, so that is it. That's the complete implementation of the CVSD soundboard, and it works. It works fine. It works perfectly. And so right now, what I'm doing with this is I might come back to this and try to tweak this a little bit more because I had some timing issues on other parts of the core. So I was working on that for a little bit. I'm also working on a new version of the TMS CPU. It'll be my third revision of it. Hopefully this one is like basically what I like to do is I try to come up with several versions of an implementation, and I try to figure out, oh, is there any way I can improve upon this? Is there any way I can perfect this, right? And try to like kind of keep perfecting it if I see problems. If I don't see any problems, then I'm done, right? It works fine. I can go ahead and release it. But if I see like that there's problems with the timing and all that stuff, and there's like glitches happening. So in this case, the sound works perfectly, but like what happened was because I had timing issues, like only one speech sample would play, and that would just like it would just like stop playing. It's really weird. So I had some weird issue because of the timing of something that was going on. The audio would play just fine though. The music would play, the instruments would play, everything else would play. Just the speech would like it would play one sample and it would just like stop. So I attributed that to a timing issue. I traced it back. It took me like a few days to try and trace it back and figure out what was going on. A lot of trial and error there, and I found it was a timing issue. So now I'm trying to work out broader timing issues in my main CPU core, which I have some timing issues there, and then also in my in the rest of the core as well. So just trying to kind of perfect it and get it to a point where I can use it generically across multiple projects. So that's usually what I do. Okay, so it was nice talking to you about this topic. Hopefully, this helps you out on your journey in terms of modeling schematics and that sort of thing in HDL. And so I'll see you in the next video.